Hello friends, I am Dr. Gaurav. In this video, I will discuss about Rankine cycle. Contents are Rankine cycle, performance parameter of Rankine cycle, effect of operating variables on Rankine cycle performance, Carnot Vapour power cycle comparison with Rankine cycle. Rankine cycle. It is the ideal cycle for vapor power plants. The ideal Rankine cycle is shown schematically and on a pressure volume PV, temperature entropy TS and enthalpy entropy diagrams. Here small v represents specific volume, small s represents specific entropy, small h represents specific enthalpy. That is, these are in per unit mass. This is the Rankine cycle block diagram. This is the TS diagram. This is the PV diagram, and this one is the HS diagram. There are four main components in Rankine cycle. First component is boiler, second is turbine, third is condenser, fourth is pump. To draw the TS diagram, first you need to draw the dome. This is the dome. The maximum point on the dome is known as critical point. Then you need to draw the two pressure lines. First pressure line is from 4 to 1 double dash. This one. 4 to 1 double dash. That is, any point on this line will have the same pressure. And the second pressure line need to draw is this one. 3 up to this point. So this is again a pressure line. Constant pressure line. If you want to go beyond this point, then you have to draw line in this way, similar as that of 1 dash. And if you want to go on the left side from point 3, then you need to draw in this way, similar as that of this line. Next, to draw the PV diagram, again you need to draw the dome, this one. Then you need to draw two pressure lines, 4 1 dash and 3 2 dash. To draw the HS diagram, again first of all draw the dome. This is the dome. Then draw two pressure lines, 4 1 dash line, 1 double dash line and 3 2 double dash line. This one. Now in order to plot the points 1 1 dash 1 double dash 2 2 dash 2 double dash 3 and 4, we will discuss these in later section. It is clear from the figure that if at the entry of turbine the condition of the steam is wet, that is point 1 dash. 1 dash represents wet point at the entry of the turbine. Then the cycle followed will be 1 dash 2 dash 3 4 1 dash 1 dash 2 dash 3 4 1 dash. For dry saturated steam, then the cycle followed will be 1 2 3 4 1. So if the entry point of the turbine is dry saturated, the cycle followed will be 1 2 3 4 1. If the entry point to the turbine is superheated vapor, then the cycle followed will be 1 double dash 2 double dash 3 4 1 double dash 1 double dash 2 double dash 3 4 1 double dash. This will be followed when entry point to the turbine is superheated steam. In Rankine cycle, steam is used as working substance. Many of the impracticalities associated with the Carnot cycle can be eliminated usually by superheating the steam in the boiler and condensing it completely in the condenser. Means in case of Carnot cycle, Carnot vapor power cycle, there is limitation for point 1. This point 1 can be here only. It cannot go beyond, means it cannot go on the right side. It cannot become superheated steam. But here in Rankine cycle, this point 1 can be superheated steam. That is, it can be 1 double dash. And the second condition is condensing it completely in the condenser. So in case of Carnot cycle, our point 3 is somewhere here. But in this Rankine cycle, our point 3 is here. So our point 3 will become saturated liquid. All four components associated with the Rankine cycle, that is pump, boiler, turbine and condenser, are steady flow devices, and thus all four processes that make up the Rankine cycle can be analyzed as steady flow processes. The kinetic and potential energy changes of the steam are usually small relative to the work and heat transfer terms and are therefore usually neglected. Then the steady flow energy equation per unit mass of steam reduces to heat in minus heat out plus work in minus work out equal to enthalpy associated with the exit steam minus enthalpy associated with the inlet steam. The ideal Rankine cycle consists of the following four processes. Below analysis is done by assuming that steam enters the turbine as dry saturated, that is, follow the cycle 1, 2, 3, 4, 1. So the first process is process 4.1, constant pressure, that is isobaric process, P1 equal to P4, heat addition in the boiler. So you can see here first process is 4 to 1. This is constant pressure heat addition process. So in the boiler we are supplying the heat at constant pressure so that the point number 4, which is a liquid point, will become point number 1, that is dry saturated. So you can see in the TS diagram, point 4 is liquid point when we supply heat at constant pressure. So this is the constant pressure line. Then this point will become point number 1. So in this way we can draw this point, or we can plot the point 4 and 1. Similarly on the PV diagram, this point 1, 4, and on the HS diagram point 4 and 1. Also remember that P1 equal to P1 dash equal to P1 double dash equal to P4, because this is a constant pressure line, and T1 equal to T1 dash. So in this case what we are having? We are having W in equal to W out equal to 0 and Q out equal to 0. So this value 0, this one 0 and this one 0. What left? Q1 is equal to H exit. Exit is point number 1. So H1 minus inlet point is point number 4. So H1 minus H4. So Q1 equal to H1 minus H4. Next process is process 1-2, isentropic constant entropy expansion in turbine. So you can see here 1, 4. So there is isentropic expansion, that is entropy will remain the same. So here the dry saturated steam will enter the turbine, where it will strike the turbine blade and the turbine blade will rotate, due to which will get the work turbine out, and point number 1 will become point number 2, and there is a expansion of the steam. So you can see in the TS diagram the process is isentropic, that is constant entropy. There will be a vertical line from point number 1 such that it will cut this second pressure line at point number 2. So we will get the point 1 and 2. Similarly for this PV diagram, the nature of constant entropy line is this one, curved line. So 1, 2. And in the HS diagram, again we'll get the vertical line from 1 to 2. Now, we are getting the work, so our work will be positive. So in this process, Q in is equal to Q out equal to 0 and W in is also equal to 0. So if we apply this condition, this quantity 0, this one 0 and this one 0. So minus W out will be equal to H exit is H2 and H in is inlet is H1. So H2 minus H1 equal to minus W out. So minus W out, or we can say W out, will be equal to H1 minus H2. H1 minus H2. Next process is constant pressure, that is isobaric, P2 equal to P3. This is in the subscript, that is heat rejection in the condenser. So process 2-3, we are having condenser as the component, so there will be heat rejection from the steam. So what we get? We are getting a constant pressure heat rejection process. So this is point number 2, this is point number 3, and it will be a horizontal line because in between the dome we are having constant pressure line as the horizontal line. So this is point 2 and 3. We are taking the heat from the wet steam point, that is point number 2, and so that our wet steam will become the saturated liquid, that is point number 3. So in this, W in equal to W out equal to Q in equal to 0. Only we are having Q out. So W equal to W out equal to 0 and Q in equal to 0. So if you apply this condition, W in equal to 0, W out 0 and Q in 0, then minus Q out is equal to at H exit. Exit means point number 3. So H3 minus H inlet. Inlet is point number 2. So H3 minus H2 equal to minus Q out. So Q out will be equal to H2 minus H3. H2 minus H3. It can also be represented as Q2 equal to area under the line 2, 3 in the TS diagram, that is TL ds. You can see this is a vertical line 2, 3. Sorry, this is a horizontal line 2, 3. So the area will be height into width. Height will be TL. So TL is equal to T2 dash T2 T2 double dash T3 equal to TL. Multiply width, which will be S2 minus S3. So what we get? We get this formula as TL ds equal to T2 into S2 minus S3. Next process is process 3-4. Isentropic constant entropy compression in the pump. So point number 3 is saturated liquid. So we are setting a saturated liquid in the pump and we are supplying W pump work into the pump, into the system, that is pump, so that our point number 3 will become point number 4. So there is a isentropic compression of this saturated liquid from 3 to 4. So this line will be a vertical line 3-4, and in this 3-4 line is this one isentropic process, and in HS diagram again we will get the vertical line 3-4. You can see we are having only W in. W out is equal to 0, Q in is equal to 0 and Q out equal to 0. So what we can say? We can say that if we apply this condition here, Q in equal to 0, Q out equal to 0, W out equal to 0. So W in is equal to X exit. Exit is point number 4. So H4 minus H inlet. Inlet is point number 3. So H4 minus H3. So this is, we get H4 minus H3. We know that for flow process, W in is equal to W pump in equal to integration of VdP, where V is specific volume. So as we know that for the liquid the specific volume is almost remain the constant, so it will be out of integration. So the formula will become V P4 minus P3. But you have to remember that unit of pressure must be in kilopascal, so that W pump in will have the unit as kilojoule per kg. Next is performance parameter of Rankine cycle. Thermal efficiency of Rankine cycle is given as net work done divided by heat supplied. So net work done is given as W turbine out minus W pump in divided by Q1. If you put the value of the work and the heat supplied, you will get this formula. Since feed pump work is very small compared to the turbine work, so sometimes this W pump in is also neglected. So you will get this formula. But remember that unit of pressure must be in kilopascal, so that W pump in have the unit in kilojoule per kg. Next is work ratio. The formula of work ratio is net work done divided by turbine work. Net work done is given as W turbine out minus W pump in divided by W turbine out. Putting the value of work, we will get this relation. A low work ratio implies large pump work. Large the pump work, lower the work ratio. Next is steam rate or specific steam consumption, SSC. It is defined as the ratio of steam flow rate divided by power output, and the unit will be kilowatt hour. So the formula will be 3600 divided by net work done. 3600 divided by W turbine out minus W pump in. It will be kilogram per kilowatt hour. So what we can say? Why we are taking this 3600? Because in 1 hour we are having 3600 seconds, where the net work done is in kilojoule per kg. Next is heat rate. Thermal efficiency can be expressed as heat rate, which is a measure of the rate of heat input Q1 required to produce unit work output, that is 1 kilowatt. So heat rate formula will be 3600 multiply Q1 divided by net work done. So we can say 3600 divided by efficiency, this one. So unit will be kilojoule per kilowatt hour. Next is effect of operating variables on Rankine cycle performance. Steam power plants are responsible for the production of electric power in the world. Therefore, every effort is made to improve the efficiency of the cycle on which steam power plants operate. There are three ways of accomplishing this for the simple ideal Rankine cycle. From the TS diagram of Rankine cycle, we can derive efficiency of Rankine cycle as below. Efficiency of Rankine cycle is W net divided by heat supplied. W net is Q1 minus Q2, that is heat supplied minus heat ejected divided by heat supplied. So we can say the formula will become 1 minus heat ejected divided by heat supplied. So if you put the value of heat ejected, the formula is TL S1 minus S4. So here there is a mistake. Convert this into, this formula will be S2 minus S3. So here we are having S2 minus S3. If you go S2 equal to S1 and S3 equal to S4, so this will become S1 minus S4. And for the heat supplied, there is a formula average or mean temperature of heat addition into S1 minus S4, because you can see in the TS diagram this temperature is varying, that is from 4, 1 dash 1 and 1 double dash. So this temperature is varying, so we have to take the mean temperature. But for the process 2 dash 3 or 2 3, or we can say 2 dash 3, we are having a horizontal line, that is a constant temperature equal to TL. So we have taken TL here, but we have taken T mean for this variation from 4 to 1 dash or 4 to 1 or 4 to 1 double dash. So we have taken the mean value for this one and lower temperature for this one. And also remember that S2 equal to S1 and S3 equal to S4. So what we get finally? Finally we get this formula 1 minus TL divided by Tm, where the TL is the temperature of heat ejection and Tm is the mean temperature of heat addition. Next is increasing the boiler pressure, that is increasing T higher average, that is we are increasing this value of Tm. By increasing the boiler pressure, the mean temperature of heat addition increases and thus raises the thermal efficiency of the cycle. So by doing so, we are increasing the value of Tm. So when the value of Tm increase, then the value of efficiency will also increase. So you can see this 1, 2, 3, 4 is without increasing the boiler pressure, and this 1, 2 dash, 3 dash and 4 dash is with increase in the boiler pressure. Notice that for a fixed turbine inlet temperature, that is we have taken this 3 and 3 dash on the same level, T3 equal to 3 T3 dash, and condenser pressure. So we have taken the same condenser pressure. This line is same. Only there is a variation in the boiler pressure. This cycle shifts to the left. So you can see our previous cycle was 1, 2, 3, 4, and our new cycle is 1, 2 dash, 3 dash, 4. So our cycle shifts towards left, and the moisture content of the steam at the turbine exit increases. You can see in the previous cycle the point 4 is here, and in this cycle the point 4 dash is here. So our point shift towards the left. It means that the dryness fraction value decreases. Here the value will be less than the value at point 4. This undesirable side effect can be corrected, however, by reheating the steam. So don't worry about the points. In this cycle we have taken 0.1 here, and in this cycle we are taking 0.1 here. So there is no need to be worried about this point. You can assume this point as the point number 3 also. The net work done by the cycle remains almost same. Thus, the Rankine cycle efficiency increases with an increase in pressure or boiler pressure. So you can see by shifting towards the left, here there is a decrease in the work, but here there is an increase in the work. So the net work done of the cycle will almost remain the same. Operating pressure of boilers has gradually increased over the years from 2.7 megapascal in 1922 to 30 megapascal today, generating enough steam to produce a net power output of 1000 megawatt or more in a large power plant. So you can see we are generating a power output of 1000 megawatt or more. Today many modern steam power plants operate at supercritical pressure, that is pressure greater than this value. So our cycle will be like this, and have thermal efficiency of about 40% for fossil fuel plants and 34% for nuclear power plants. So you can see there we can get a maximum efficiency of 40% in case of fossil fuel like coal, and 34% for nuclear. The lower efficiency of nuclear power plants are due to the lower maximum temperatures used in those plants for safety reasons. So this is the overall effect of increasing the boiler pressure. Next is lowering the condenser pressure, that is lower the value of T lower average. For comparison purpose, the turbine inlet is maintained the same, because in this case we have taken the upper part same. The colored area on this diagram represents the increase in net work output as a result of lowering the condenser pressure from P4 to P4 because as we have lower the condenser pressure from P4 to P4 so there will be increase in net work we are getting. The heat input requirement also increase, represented by the area under the curve 2 and 2 So heat input requirement increase and our net work also increase, but this increase is very small. So increase in heat input is very small as compared to increase in work net. Thus the overall effect of lowering the condenser pressure is an increase in the thermal efficiency of the cycle. So overall, because the formula of the efficiency is W net divided by heat supplied. Here W net is increasing, but heat supplied is also increasing, but increase in work is more than that of the heat supplied. So the overall effect will be increase in the efficiency of the cycle. Limitation of this method are lowering the condenser pressure cause an increase in moisture content of the steam leaving the turbine. It is an unavoidable or unfavorable effect and may lead to the turbine blade erosion. So you can see point 4 and 4 dash. At point 4 dash, the dryness fraction value is less than that of the point 4. So when the value of the dryness fraction decreases, so there are chances of turbine blade erosion. To maintain high vacuum, the air extraction pump will run continuously and its work input will increase, thus reducing the useful work. So, in order to maintain lower pressure in the condenser, that is this pressure P4 dash, we have to use a extraction pump, air extraction pump, and for that we need to supply the additional work. Next is superheating the steam to high temperature. Increases T higher average. The colored area on this diagram represents the increase in net work. So, our previous case was 1, 2, 3, 4. Now our new case is 1, 2, 3 dash 4 dash. So there is a shift, or our diagram will shift towards the red, that is from 3, 4 to 3 dash 4 dash. Thus both the net work output and heat input increase as a result of superheating the steam to a higher temperature. So our heat supplied will also be increased, that is in the previous case it was from 2 to 3. From 2 to 3. Now our in the new case it will be from 2 to 3 days. So there is an increase in the heat input, but also there is an increase in the work, net work we are getting from the cycle. The overall effect is an increase in thermal efficiency, because the formula of the efficiency is W net divided by heat supplied. So here the heat supplied is increasing, but work net is also increasing. The increase in work net is more than that of the heat supplied. So the overall effect will be increase in thermal efficiency. However, average temperature at which heat added is increased. So our average temperature increased from 2 to 3 dash. In the previous it was 2, 3. Superheating the steam to higher temperature has another very desirable effect. It decreases the moisture content of the steam at the turbine exit, as can be seen from the TS diagram. So when we are getting point 3 and 4 dash, you can see at point 4 dash the value of dryness fraction is more than that of the point 4. So there will be less moisture at the point 4 dash. So there are less chances of blade erosion. The metallurgy consideration restricts the superheating of steam to a very high temperature. So we cannot, there is also limit for 0.3 dash. You cannot go beyond this point. So there is a limit for 3 dash also. So again I am repeating, don't worry about the points. Initially we have taken this one as the point 1 dash 1, or we can say this point as the 3, but here we are taking this point as the point 1. So you can say this point is 3, 4, 1, 1 dash 2 dash 2. So don't worry about the point notation. Our conclusion for the three cases we have done, that is increasing the boiler pressure, this one, second lowering the condenser pressure, and third one superheating the steam. Our conclusion, we can conclude that efficiency of Rankine cycle can be increased by lowering the condenser pressure, by increasing the boiler pressure, and by superheating the steam. The quality, that is dryness fraction of steam leaving the turbine, decreases by lowering the condenser pressure and by increasing the boiler pressure. while it improves by superheating. Next is the comparison between Carnot vapor power cycle and Rankine cycle. So point one is for Carnot vapor cycle, it is a reversible cycle. Rankine cycle, it is an irreversible cycle. Actual Rankine cycle is irreversible cycle. It has theoretical maximum efficiency. So Carnot cycle has theoretical maximum efficiency. Rankine cycle has less thermal efficiency than that of the Carnot vapor cycle. In Carnot cycle, heat is added at constant temperature. In Rankine cycle, heat is added at constant pressure. In Carnot cycle, use of superheated steam is practically difficult. So we are not getting the superheated steam. We are getting maximum up to dry saturated steam. But in case of Rankine cycle, we can use superheated steam and perform better. In Carnot cycle, controlled condensation is required before being saturated liquid, because in this cycle, Carnot cycle, point number 3, that is leaving point of the condenser, is wet point, whereas in case of Rankine cycle, complete condensation of steam takes place, that is point 3, which is leaving point of the condenser, is saturated liquid. In Carnot cycle, mixture of water and steam exists after condensation, that is point 3. Only saturated water exists after condensation, that is point 3, leaving the condenser. Carnot cycle requires a large pump work to handle the two-phase mixture, because point number 3, which is leaving point of the condenser, is having or is a wet point. So for a wet point, the value of the specific volume is large. So to handle the large specific volume, we need to have a large size of compressor. Whereas in case of Rankine cycle, it required negligible pump work to handle the liquid water only, because point number 3, leaving point of the condenser, is a saturated liquid point. Carnot cycle require a large pump work to handle the two-phase mixture. We have already discussed this point. Next is Carnot cycle uses saturated steam. The moisture content at the end of the expansion is much higher, which can lead to blade erosion. So there are chances of blade erosion in case of Carnot cycle. But in case of Rankine cycle, we generally use superheated steam in the cycle, and at the end of the expansion, the quality, that is dryness fraction of steam, is not objectionable, means it will have higher value of dryness fraction, so there are less chances of blade erosion. Carnot cycle is a theoretical cycle and cannot be used in practice. Rankine cycle is used in almost all thermal power plants, operates on Rankine cycle. These are the references used in the video. Thanks. Any questions you can write to me gaurav.citem@gmail.com.